Yeah, I would like to start with the definition and with emphasizement of classic fiber sensor. So here we detect reflection or transmission shift due to changes in transmission in temperature or strain. So this is represented by fist hitting a fiber here. So typically we use fiber break ratings. So in other words, we use classic fiber sensor and use fiber intrinsically as a sensing device. But here at Keystone Photonics, what we do is we produce a fiber probes. So instead of using fiber themselves, we use end of fiber, so fiber tips. So we use additive technology of 3D laser printing. Basically, we also use femtosecond lasers, but instead of inscription, such as Alphanov company does, we do additive manufacturing of polymer lenses. And we do not really attach fiber lenses, but we fabricate in situ. So we really detect cores of fibers and fabricate polymer micro-optics in situ and use them as sensing devices. So this is more illustrative example of our approach, of Keystone approach. Here you can see two typical structures printed by Keystone Photonics. So this is a cross section of a fiber array, and first structure represents freeform structure. So this is a globe, and the second fiber was used for printing a periscope lens that focuses light into this globe. And basically what we can produce at Keystone Photonics is any kind of freeform optics. So we now focus on refractive optics. We produce different micro lenses with reproducible beam shapes and beam expanders. And this is not really a marketing image. What we can do is really focus light into Karlsruhe, Germany, where Keystone Photonics is situated. So we are fast growing startup. There are around 10 people in it. And yeah, so speaking about industrial applications, we provide innovative solutions for optical coupling, and based market is wafer level testing. So here you can see two typical products. So we fabricate lenses on fiber arrays for both grating couplers solutions and for trench coupling, where we can deflect light by 90 degrees or by any artificial angle. We can also fabricate beam expanders, and we can produce mode field diameters starting from 2 microns up to 15 microns of mode field diameter. If we compare our technology with conventional technology for wafer level testing and for optical coupling, I want to emphasize these graphs. So this is coupling efficiency versus positional misalignment, and the red curve represents variation of coupling efficiency using Keystone lensed fiber probes, and gray curve is just bare fiber arrays, when you move the bare fiber array as close as possible to the wafer. And as you can see, so using just normal technology, you are prone to variation in coupling efficiency, and our printed lenses have much better coupling efficiency and less prone to variation. And this is for grating coupling approach. For edge coupling, our solution is basically the only one, because the only possible alternative to edge coupling is using a 45-degree polished fiber array. And here you need to move as close as possible the fiber array to your edge, to the waveguides, and um, using our approach, we can achieve up to 1 decibels of coupling efficiency, and using the standard approach, you will achieve something 4 dB, with very large variation. And if you want to improve coupling efficiency using the standard approach, you basically crash the fiber array into trench. So our solution provides very efficient method of optical coupling using trenches and edge coupling. So we are currently dominating the market for lensed fibers. We are collaborating with many major players in wafer level testing area. So we provide our lens fibers to form factor, to Phi contact, to MPI testers, and to many other photonic companies in the photonic industry. But since this meeting about fiber sensors, I'd like to introduce also a real optical distance sensor. So this is our latest development. Here we actually, the idea of this distance sensor was born when we faced the challenge in wafer level testing first. So here you need to understand the distance between fiber and your chip. And basically, what people typically use in this area is they use an extra capacitive sensor or additional distance sensing device, which is very difficult to align. It costs money and yeah, it's simply ineffective. So we decided to kind of build a solution for optical distance sensing. So this is just a lens printed on a fiber array, and using a confocal principle, we can scan the lens, scan the fiber array, or just a bare fiber, along the z-axis, so up and down here, and we can measure back reflectance or back coupling efficiency. And this is the graph, the example of this kind of measurement. And here, if you achieve the point of best coupling, you achieve the distance when the distance between lens and your fiber, distance between distance between the lens and the chip equals to working distance of the lens. So meaning that we can calibrate this distance and calculate distance without using any extra capacitive or external sensors, which is very promising approach. First of all, in wafer level testing, but we also believe that this approach can be used in different areas. Also, just to one comment, referring to the previous speaker, so here we can also create a Fabry-Perot cavity between the lens and the chip. So here you can also see the interference patterns that caused by Fabry-Perot cavity. So in this case, this is rather noise than a helpful feature, but we're currently studying it in more detail. So what can we offer is 3D printed micro-optics based on your design. So we provide solutions for fiber arrays up to 64 channels. We also work with different wavelengths, starting from visible light up to 2 and plus microns of wavelength. We directly print them on fiber arrays, and what we're looking for is, so we do not really want to limit ourselves to wafer level testing, but we currently looking for new applications. So for example, we can also print lenses on fiber break gratings as well and use them for some kind of spectroscopy. Or we can also study viruses and so on. So if you have any ideas on how we can enhance or how can we be helpful in your application and with our 3D printed micro-optics attached to fiber facets, please reach us out and or just write to us, and so I'm happy to answer questions. Thank you.